So to keep things shortly, the first part of this Mathcad paper is containing the same important parts as previously. So it has a title which describes what circuit is going to be calculated here, the name of the author, the date when I did this paper, and I have the introduction part where I declared all the circuit parameters. For instance, my input voltage, I have the capacitor value, the resistor value, the tolerances then are used for being able to calculate the maximum and minimum value of the resistor and of the capacitor. And then let's start to analyze this circuit. And the first case is allocated to an ideal approach of this circuit where we don't take into the consideration the parasitics that could be present in this circuit. And we could see that the formula that actually from the book, from the lecture, is very simple, and it doesn't contain any parasitics and provides the output voltage and doing this calculation, this parametric calculation where I define t, the parameter t, which is the time as a parameter. And by doing the calculation in this way, it is very easy for us to see what could be this output voltage at different moments in time, for instance, 10 milliseconds and so on. On the next part, I'm going to plot this output voltage for this ideal case. And what you have to know, for instance, when you do plotting in a PTC Mathcad is the fact that you have to declare the x-axis, which in my case is time, and I declare the range from 0 to 10 milliseconds in steps of 0.1 milliseconds. And on axis Y, I have the voltage because I do a representation of voltage over time. Another thing is that to make the representation to look a little bit realistic, considering that I have an amplifier that has a positive supply and a negative supply. And this being an inverting integrator, the output will decrease over the time. And it is known that at the moment when the output voltage is reaching the negative supply, the amplifier will saturate and the output voltage will stay at the value of this negative supply, which is minus 6 volt. How I tried to implement this in Mathcad. So I did an attribution where the output voltage of this ideal case will always take the maximum value of its value, or will take the maximum between its value and minus 6. Because we know if we are above minus 6, then the output will start decrease, and then once it reaches minus 6 and it goes below minus 6, it stays there. So it will always be equal to minus 6. You can do this, as I said, either by calculating the maximum between the current value of the voltage itself and the minus 6, or you could implement some if logic where you say if this output voltage is lower than minus 6, then the output voltage should be minus 6, otherwise it will be its current value. And you see that I have a representation of the V out versus time. I could say that looks pretty good and pretty realistic, but this is not really realistic. The next part of this paper is going to show you what is going to happen and what is the difference in the output voltage when we consider some parasitics of this circuit. And we, as hardware engineers, when we do an analysis of a circuit, we have to consider or to have in mind these parasitics. And for instance, for this case, I considered some values for the input bias current and input offset current and voltage and the output offset voltage. I took these values as an example to help us to understand how the formulas change and how the end result change in case we consider all the parasitics. And here I calculated the input bias currents for both inputs of the amplifier, for the negative and for the positive input. And then using the second method, I calculated the output voltage which I called it now output voltage real because it's a realistic situation where we included the parasitics of the circuit, and we could see that our formula now looks much bigger and a little bit more complicated. This formula, how I got this formula was by doing some hand writing calculations, and here you have the end result of it. Here we could identify two parts of this formula. So the first part is identical with the ideal case where the parasitics were not considered, and the second part of the formula is containing the contribution of these parasitics. We could identify the bias current, offset voltage. By doing that approach shown in the voltage divider example, we can get the maximum and the minimum values for this output voltage, and here I calculated at different moments in time to see the values of it and to see the trend of it. Next, I'm going to show you how you can plot this output voltage. In PTC Mathcad, it's possible to plot a waveform, either referring to the name of it, or you could also plot it by typing here in the plot on the right side the formula, and the tool will know how to calculate this function and then to plot it over the time. And here I plotted the nominal case of the V out for the ideal approach, and the nominal case for the V out for the, let's say, realistic case. The ideal case is plotted with a blue line and the realistic case with a red line. And then we could see that there is a slight offset between the ideal and realistic case, because parasitics plays a role here, and this is why there is this offset, because parasitic components, which are the output offset voltage and the input bias current. But of course, you could do this kind of representation in a much nicer way without inserting here the formulas, just referring to the name of the function that you are representing, and just placing the index, let's say nomi, for referring to the nominal case. Of course, we could represent, we could do different representations to compare nominal versus maximum, and so on. Thank you for having patience to follow me in this presentation.